Okay, let me solve a numerical on basically a thick cylinder. Thick cylinder equation, I mean, there are two types of stresses basically. The longitudinal stress, it is constant and it doesn't vary. What varies along with the thickness of the cylinder are these two stresses, radial stress and circumferential stress. So, first I will actually try to explain the numerical which is shown there, which is not visible in the video. It says that there is a cylindrical pressure vessel which has an inner radius and outer radius of 200 and 250. So inner radius is Ri is equal to 200 mm and R naught is equal to how much? 250 mm. Okay, and the material of the cylinder has an allowable stress of 75 MPa. It has got a, so this is slightly different from the other. So it has got an allowable stress of 75 MPa. So that means you cannot let more stress, it is almost like the design stress. So that means the maximum stress that I can apply is this 75 MPa. Allowable stress of the is 75 MPa. And determine the maximum internal pressure that can be applied. So what you need to determine is determine the maximum pressure. Determine the max pressure in the cylinder. Determine the max pressure in the cylinder. Okay. Now we just need to see here that in a cylinder which looks like this, I'm only drawing one side of the cylinder, trying to zoom it. I'll switch off this because it's not needed anyway from now. You got the cylinder here, and I'm only trying to draw one side of the cylinder, and because it will try to take a lot of space here. So this is inner radius, this is outer radius. You know, outer radius is how much? 250 mm. Inner radius is 200 mm. And then here you understand that as you start to increase the pressure, now the cylinder wants to expand its volume. Okay, so basically the inside volume has to expand. So when the inside volume wants to expand, then the stresses which are actually trying to pull the material along the circumference like this, which is called as what? Circumferential stress or the Hooke stress. And again there is a, again due to pressure here, the material is being applied with the normal stress, which is actually the compressive stress. So basically you can say that this radial stress is actually applying on each of this element here. Suppose if you can take small blocks of material here, or you can say some layers of material here, the inner layer is always applied with a compressive force here, which is given by this equation. And the circumferential stress is given by this equation. But we know that most of the cylinders actually fail by the circumferential stress, because circumferential stress is more than the longitudinal stress, that we saw last time. Circumferential stress is Td by 2T, whereas the longitudinal stress is actually given by Td by 4T. So you can say this, here there is 2, here there is 4. So circumferential stress is the one which actually makes the cylinders to fail. So therefore, you need to understand that when the circumferential stress becomes equal to 75 MPa, the cylinder is going to fail. And usually this happens at the inside of the cylinder, because the cylinder inner walls will actually stretch more than the outer walls. Okay, so this is some logic that you need to have before actually solving the problem. So what we can actually do is, so here I think here with this logic we try to set the boundary condition. So now what is the boundary condition now? As an engineer, okay, I know that there will be circumferential stress here which can go up to 75 MPa and fail. And okay, the stress, okay, is it inside or outside? Okay, is it inside or outside? It is inside. So circumferential stress is inside. Is inside. So that means you need to substitute this R value as how much? 200. You need to substitute this R value as 200, and then this value as how much you should substitute? What is the maximum circumferential stress? 75. It is given 75. You should substitute 75 here. Then you should substitute R value as 200 here. So that is one equation. So let me write this equation. So basically the boundary condition is, one boundary condition is this. So people write boundary condition. I think is this visible? No? Okay. So boundary condition. So boundary condition, people say BC I write. Okay. At R is equal to Ri. At R is equal to Ri. Sigma C circumferential stress is equal to how much? 75 MPa. And here you are writing, you know that what is actually MPa basically. So how do you convert MPa into Newton per mm square? So basically P is Newton per meter square. So you can simply write this as 75 Newton per mm square. Okay. So here you understand that the unit here is the same as the stress. Okay. So you can actually substitute this as stress here. Basically this material is actually stressed. The element at the inside of the cylinder is being stressed by a stress of 75 Newton per mm square. Okay, that is what you understand. Boundary condition is at radius equal to inner radius, the circumferential stress will increase up to 75 and fail. For that you need to find out what is the inside pressure. What is the inside pressure? But you know what will be the pressure outside basically? Is it more than the atmospheric pressure? It is atmospheric pressure. Atmospheric pressure we take it as zero pressure because we are actually taking relative pressure, not the absolute pressure. So you can say that at R is equal to R naught. So R naught refers to how much? 250. Okay, at this point, okay, that is at the that's at the outside of the cylinder. What is the pressure basically? Now what is the pressure? Now, so what is the pressure? It is zero. So we are referring to this radial stress. Radial stress or pressure, you can write it as pressure. If you suppose if you don't want to use this stress word, you can use this word pressure, radial pressure. So from outside the pressure is zero. So I need to use this equation where I substitute this R as how much? So much I should substitute. So that is 250. I should substitute at 250. That means when R is equal to 250, the radial stress is equal to 0. So I get actually two equations here. So one is this first equation using this. So if I now substitute this, now as per the first equation, what do I write? Sigma C is equal to how much? 75 Newton per mm square. Sigma C is equal to 75 Newton per mm square, which is equal to A plus B. I don't know what is the value, but now what is the value of R? 200 square. So don't worry about the units. So units, you understand what is the, now whatever the answer is that you get here will be the same units. Okay. Okay. So this is one equation. This is one equation. And by using the second boundary condition, what you are writing? Now what is this? Instead of sigma C, what I should write? I should write P is equal to how much? So radial stress P is equal to how much? 0 MPa. 0 MPa means 0 Newton per mm square. 0 Newton per mm square. It is minus A here plus B divided by how much? 250 square. Sorry, you don't have to worry about the units here. Okay? So 250 square here. Here if it is an mm, Okay, here also it should be an mm. Okay, so see that you substitute properly. Okay, newtons and mm. So now you got basically two equations to solve. Guys, until now is the engineer's work. Engineer has done, has analyzed and has made this equation. From now onwards, it is anybody's job to solve this equation and come out with values of A and B. And again at the end you will have engineer's job where they will interpret, where they will use the values of A and B to find out the stress. So that is this radial stress at the center, because if you substitute, here you substituted 250 earlier, again you can substitute, once you have found out A and B, then you can again substitute this R value as how much? 200. That will give you the pressure which will actually produce a circumferential stress of 75 MPa. Okay, so we need to solve this equation. So is it visible here? If I write here, is it visible? Okay, now since it is visible, we'll go ahead. Okay. Now I'll write this equation once more here. Okay, shall I erase this? I'll write this equation here to solve. So sigma c, 75 equal to A plus B divided by 200 square, and the one more equation is 0 equal to minus A B 250 square, here it's square. Okay, there are two equations here to solve, this equation and this equation, equation 1 and equation 2. Guys, can we solve this simultaneous equation? Can you tell me? Okay, now if you add this, adding 1 and 2, so what will you get? If you add this 1 and 2, you will have to add the corresponding elements. 75 is equal to plus A minus A, how much? 0. And then what is B plus 200 square plus B plus 250 square. Okay, so what you have is, so you can take this, the denominator 200 square 250 square, and then multiply here. So you can take this B outside, and then so 250 square plus 200 square, so that's equal to 75. So you can write this, of course you can take this B outside, and then you can write this as 1 by this one, and like this you can do, because B is common. So what is the value of B? Huh? Do we get a very large number? Huh? So please. Huh? 1? 18? 29? 26? That's it? 0.2. Okay. So usually you get a larger, 268.2. Okay. 182,926, 8.2. Okay. You got a large number, no units, it's just a constant. So once you have got this, then now this can be used to, so you can call this as 3, substitute this value of 3 in any of the equations, 3 in 1 or 2, in any of these equations, you can get the value of A. Substitute it here. Okay, suppose if you want to substitute in this, equation 2, so 0, so I'm going to substitute 3 in 2, 0 is equal to, I don't know the value of A, so the value of B is 1829 268.2 divided by 250 square. So what is the value of, so you can take this A to the side. What is the value of A? Guys, what is the value of A? Is it seen? Is it visible in the video? Okay. 29.26. So you get this one more number here. 29.26. So it is like you have done almost around 60% of the problem, because finding out A and B is actually the main part of the problem here. The rest is to use this value of A and B in solving for the unknowns here. So here what we knew was that outside the radial stress P was 0, the inside sigma was how much? 75 MPa. Inside the sigma C was 75 MPa, outside radial pressure was 0. But I don't know what is the value of P inside and sigma C outside. Now, since I know A and B, since I know the value of A and B, okay, here this equation basically is, now this equation is sigma C is equal to plus A B by R square. Here this is actually P is equal to minus A plus B R square. Okay. So now I can substitute these values of A and B along with radius. So here I know only sigma C inside. What is the sigma C outside if you want? Now what you should do? So you should actually, so shall I erase this part of the, is it seen? Okay, is it visible up to you? Okay. So now what I will do? So now I'll go for the sigma C value. Sigma C at R is equal to how much? 250. I want, because it was known that, I think as an engineer, I knew that the maximum tensile stress would be at the could be at the inner surface, which would actually make this to fail. It was not explicitly given in the problem. It was said that the material has got a maximum stress of 75. But I know that as an engineer, the inside fibers will actually stretch more than the outside fibers. So I have taken this value as 75 for the inner. If I want it for the outside, then sigma C at R is equal to 250. What is the equation? What is the equation? So that is given by, so what is the value of A? 29.26 plus B. What is the value of B? It's a very huge value. 182926.8.2, and here this R has to be substituted as how much? 250 square. That will give you sigma C at, so R is equal to 250. What is the value, man, here? 58.5. 58.5. Guys, what was the stress inside? 75. So that means outside the stretching in the circumferential direction has reduced. This is Newton per meter square or MPa, because they are same. Okay. So you can write MPa because it was given in MPa. Okay. So you found out this. And then one more has to be found out. Can you tell me? 75 inside sigma C was found out. Sigma C outside is found out to be how much? 58.5 MPa. And then outside pressure P is known. Do we know what is the inside pressure? That is what is required, because it was asked in the numerical, determine the inside pressure, which will actually produce this sigma C of 75 at the inside. So I want the inside pressure P at the inside If I want P at the inside, which equation I should use? Equation 1 or 2? So you should use equation 2. Equation 2 it will give you this value. So, is it visible here? Okay, I will try to erase this point, erase this and try to do. So, we'll use this equation here. We'll use this equation. Okay, so I want the pressure inside. So, pressure inside means I want this P at R is equal to how much? 200. So, P is equal to what? Minus A. What is the value of A? 29.6. So 29.26 plus what is the value of B? B is a very large value, 1829.268.2 divided by R. What you should put? 200. 200 square. Can you tell me the value of P that you get? Huh?
16.47.
16, huh?
Yes, sir.
16.47 MPa. So that means 16.47 MPa of internal pressure, 16.47 MPa of internal pressure would result in the stretching of the material in this direction, which is equal to 75 MPa, which is the maximum. So therefore, you can say that at the maximum you can apply a pressure of how much? 16.47 MPa before the cylinder fails. Okay, because we know that the internal pressure, the internal stress is 75, circumferential stress is 75, outside is 58, which means that is more always here. So therefore, you have got these values. Usually in the examination, even if you have solved all this, you may not get full marks or you may lose all the marks because the examiners are waiting for some answer. What is that answer? Basically, they are trying to find a way of trying to get these answers in a very short, just in one side. So for that, you should help the examiner by trying to draw this cylinder pressure variation. Cylinder pressure variation. I am only drawing the one side of this cylinder. Okay. This is the zero line. This is the zero line. That is the zero line. And there are two stresses varying here. What are that? One is P and other is sigma C. Sigma C is tensile. I will try to, we have already seen that the tensile stresses are positive because that increases the length. Okay, we will try to draw the positive stresses above, the negative stresses below. Negative means what? Compression. So pressure acting at this point will compress the material. So those are actually negative, which actually decreases the size. So positive stresses above and negative stresses below. Okay, you tell me what is the maximum, what is the positive stress or sigma C at the inside? Sigma C inside is 75. So you said it is 75. So for 75 you can draw a line which is approximate, you draw some line and say that this value is how much? 75 MPa. What is the stress outside that you got? 58.5. 58.5. You draw a line like this. Okay, 58.5 MPa. Now the variation is actually parabolic because you have got this term here. In this you got this r square term, no? So therefore it will not be a linear line here. So you can't join this with the line. So you have to join, you have to draw a curve to show that the variation is parabolic. Something like this. Okay? This is called, this curve is the variation of, so instead of actually hatching like this, people show that this is the tensile stress like this. This is the tensile stress applied on the material like this. Okay? And then you can write this is the what? Now what stress is this? Circumferential. Is it seen in the camera? Circumferential. You can write this as a circumferential stress. Okay? And then one more thing. Radial stress, which is the compressive stress. What is the maximum compressive stress at the inside? How much? How much? We just found out. 16.47. 16.47 like this. You can draw and mark this as 16.47. You don't worry. This is a different scale, this is a different scale, okay? It's left to you whether you want to take it small or large, okay? 16.47 here. And what is the stress? What is the what's the radial stress outside? It is 0. So it varies from 16.47 to 0 here. And should this be a straight line? No, again it's a parabola because the variation is it's second order. So therefore the variation is not linear. Okay, it varies like this. So what I should actually write this as? Here you write it as circumferential stress. Here you should write this as radial stress or pressure, because this is actually the pressure from inside. So pressure and stress have the same unit, so you can interchangeably use it. Okay. So again, I think some people draw arrow marks like this, which may actually lead to confusion that it is actually tensile stress. But you can actually say this actually tensile. I mean, this stress is basically acting like this. Compressive stress is something like this. You can draw. It's okay. I think people just look at how you have drawn it. What is the value here? It is 0 here, 0 MPa here. It is 16.47 MPa here. That's it. So if you now complete up to this point, you get around 10 to 12 marks. So here, basically you should know how to apply this equation. Now this equation is given by Lehm's. So these are called as Lehm's equation for thick cylinders. So you now should just remember this equation, apply this equation to solve the numerical. So we will try to solve one more numerical, so which will actually make you comfortable in understanding the boundary conditions here. Okay.